Have you ever looked up at the night sky and wondered, what's out there? It's a question that has captivated humanity for millennia. We gaze at the stars, those distant suns, and our minds reel at the sheer scale of it all. The universe is vast, unimaginably so. It's filled with billions upon billions of galaxies, each one home to billions of stars, many orbited by their own families of planets. And even that barely scratches the surface. The distances involved are so great that we measure them in light years. The distance light travels in a year. Light, the fastest thing in the universe, zipping along at a mind-boggling 186,000 miles per second. Yet it still takes light years, centuries, even billions of years to reach us from the most distant objects. This means when we look up at the night sky, we are seeing light from stars and galaxies as they were in the distant past. Some of that light has been traveling for billions of years. A cosmic time capsule from a universe long gone. To truly grasp the vastness of the universe and the question of what lies beyond its edge, we need to understand our place within it. We live on a planet called Earth, a small, rocky world orbiting an average star we call the Sun. Our Sun is just one of billions of stars that make up the Milky Way galaxy, a vast spiral of stars, gas, and dust. If our galaxy were the size of a dinner plate, our Sun would be smaller than a grain of sand. Now imagine billions of those plates scattered across a vast cosmic ocean, and you start to get a sense of the scale we're talking about. And within that almost incomprehensible expanse, we find ourselves on our tiny planet asking, what's beyond the edge? But here's the thing, the universe doesn't have an edge, at least not in the way we typically think of it. There's no signpost saying you have reached the end. Instead, the universe is constantly expanding, stretching like a cosmic balloon being inflated. To delve deeper into this mystery, we need to understand the observable universe. This is the portion of the universe we can currently observe from Earth. It's like a bubble centered on us with a radius of about 46.5 billion light years. The universe is around 13.8 billion years old. Light from objects farther away hasn't had time to reach us. The universe's expansion affects the light traveling towards us. To even begin to contemplate what lies beyond the observable universe, we need to rewind the cosmic clock back to the very beginning, the Big Bang. About 13.8 billion years ago, the universe as we know it burst into existence from an incredibly hot, dense state. In the first fraction of a second, the universe expanded at an unimaginable rate, much faster than the speed of light. This period, known as inflation, stretched the fabric of space-time, smoothing out any initial wrinkles and creating the vast, uniform cosmos we observe today. However, this rapid expansion also means that the universe is likely much, much larger than the portion we can currently observe. It's like looking at a small patch of a giant tapestry. We can only see a tiny fragment of the whole picture. The Big Bang itself left behind an afterglow, a faint whisper of radiation known as the cosmic microwave background radiation. This radiation, which permeates all of space, provides us with a snapshot of the universe as it was just 380,000 years after the Big Bang. Now let's venture beyond the cosmic horizon into the realm of speculation and imagination. What might we find in the vast expanse beyond what we can see? Well, that's where things get really mind-bending. One intriguing possibility is the existence of a multiverse, the idea that our universe is just one of many, perhaps an infinite number, of universes bubbling up within a larger cosmic foam. Each universe could have its own unique properties, laws of physics, and even different dimensions. Imagine a reality where gravity works differently, or where time flows backward, or where the fundamental constants of nature are slightly altered. These multiverse theories are highly speculative, but they offer a tantalizing glimpse into the potential vastness and strangeness of existence beyond our cosmic backyard. So we've established that the universe is vast, potentially infinite, and filled with mind-boggling possibilities beyond our current reach. But how do we even begin to explore what lies beyond the cosmic horizon? It's like trying to sail off the edge of a flat Earth. You'd never reach the end. You'd just keep sailing. The very fabric of space-time itself is expanding, carrying galaxies away from us at incredible speeds. The farther away a galaxy is, the faster it appears to be receding. At a certain distance, known as the Hubble horizon, galaxies are moving away from us faster than the speed of light. Now, this doesn't mean they're breaking the cosmic speed limit. Nothing can travel faster than light through space. However, the expansion of space itself is not bound by this rule. It's like dots on a balloon being inflated. The dots themselves aren't moving, but the space between them is increasing, carrying them along for the ride. This relentless expansion presents a significant challenge for exploring the universe beyond our cosmic neighborhood. Even if we had spacecraft capable of traveling at near-light speeds, which we currently don't, it would still take billions of years to reach the most distant galaxies we can observe. And by the time we got there, the universe would have expanded even more, pushing those galaxies even farther away. It's a cosmic game of catch-up that we can never truly win. So if physical exploration is off the table, how else can we hope to peer beyond the cosmic horizon? This is where our understanding of physics, combined with powerful telescopes and ingenious observation techniques, comes into play. By studying the cosmic microwave background radiation, the afterglow of the Big Bang, scientists can glean clues about the early universe and its evolution. Tiny fluctuations in this radiation provide insights into the distribution of matter and energy in the early universe, which ultimately gave rise to the galaxies we see today. But even with these advanced tools, we're still limited by the information that has had time to reach us. The light from the most distant objects we can observe has been traveling for billions of years, providing us with a glimpse into the distant past. What we see beyond the cosmic horizon is not what exists now, but what existed billions of years ago. For all we know, the universe beyond our observable bubble could be teeming with advanced civilizations, strange new forms of matter, or even entirely different physical laws. Some physicists have even proposed that the universe might be infinite in extent, meaning there could be an infinite number of galaxies, stars, and planets out there, many perhaps harboring life as we know it or as we've never imagined it. These ideas are certainly speculative, but they highlight the profound mystery that surrounds the universe beyond our cosmic horizon. It's a realm where our current understanding of physics might break down, where new and unexpected phenomena could await discovery. One of the most intriguing concepts in cosmology is the idea of cosmic voids. These are vast regions of space, hundreds of millions of light years across, that are remarkably empty. Imagine flying through space and encountering a region where galaxies are few and far between. These voids formed in the early universe, where slight variations in density caused matter to clump together. As matter clumped to form galaxies, it left behind these vast, underdense regions. They are thought to contain dark matter, a mysterious substance invisible to our telescopes. The existence of cosmic voids provides evidence for the large-scale structure of the universe. As we delve deeper into the mysteries of the universe, we encounter a fundamental limit: the speed of light. This cosmic speed limit governs how information travels through the universe, and it ultimately determines how far back in time we can see. But what about the regions of space so far away that their light hasn't had time to reach us yet? These regions lie beyond the cosmic horizon, hidden from our view by the veil of time. We can speculate about what might exist in those uncharted territories, but we have no way of knowing for sure until their light finally reaches us, billions of years from now. This concept of a cosmic horizon highlights the limitations of our current understanding of the universe. It's a humbling reminder that there are vast realms of space and time yet to be explored, realms that might hold secrets beyond our wildest imaginations. So what lies beyond the edge of the observable universe? The truth is, we don't know for sure. It's a realm of endless possibilities, a cosmic blank canvas upon which our imaginations can run wild. But even though we may never be able to physically explore these distant realms, we can continue to probe their mysteries through observation, experimentation, and theoretical modeling. By studying the cosmic microwave background radiation, the distribution of galaxies, and the properties of dark matter and dark energy, we can piece together clues about the nature of the universe beyond our cosmic horizon. Imagine a reality where our universe, vast as it is just one of countless others, each potentially with its own unique set of physical laws, dimensions, and even histories. The concept of the multiverse arises from several different areas of physics, each offering its own intriguing perspective on this mind-bending possibility. One such area is string theory, which attempts to unify all the forces of nature into a single, elegant framework. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings of energy. These strings, far smaller than anything we can currently observe, vibrate at different frequencies, and those vibrations determine the properties of the particles we see in the world around us. But here's where things get interesting. String theory also predicts the existence of extra-spatial dimensions beyond the three we experience in our everyday lives. These extra dimensions, curled up and hidden from view at incredibly small scales, could support other universes, each with its own unique configuration. Inflation suggests new universes constantly bubble up within a larger cosmic expanse. The implications of a multiverse are staggering. Some universes might be inhospitable, others could harbor advanced life. The multiverse, if it exists, is a tapestry of infinite possibilities. Quantum mechanics governs matter at the atomic and subatomic level. Superposition allows particles to exist in multiple states until observed. Like a coin spinning, neither heads nor tails until it lands. The many worlds interpretation suggests parallel realities for every quantum event. While the multiverse remains firmly in the realm of speculation, some scientists believe that we might be able to find indirect evidence for its existence by searching for subtle imprints of other universes on our own. One such avenue of exploration involves studying the cosmic microwave background radiation, the afterglow of the Big Bang. This faint whisper of radiation, which permeates all of space, provides us with a snapshot of the universe as it was just 380,000 years after the Big Bang. Scientists have meticulously mapped this radiation, searching for any anomalies or patterns that might hint at interactions with other universes in the distant past. Some theories suggest that collisions between our universe and other universes in the multiverse could leave behind observable signatures in the cosmic microwave background radiation, such as circular patterns of temperature variations or unexplained cold spots. While no conclusive evidence for such signatures has been found yet, the search continues, fueled by the tantalizing possibility of catching a glimpse of the multiverse through this cosmic window to the past. The concept of the multiverse challenges our very understanding of reality, suggesting that our universe is just one of countless others, perhaps infinite in number and diversity. If the multiverse is real, it paints a picture of a cosmos far grander and more awe-inspiring than we ever imagined. The idea of a multiverse, while still speculative, has captured the imaginations of scientists and the public alike, inspiring countless works of science fiction and philosophical debate. It reminds us that our understanding of the universe is constantly evolving, and that the most profound discoveries may lie beyond the realm of our current knowledge. The multiverse, if it exists, represents a paradigm shift in our understanding of the cosmos, expanding our view beyond the confines of our own universe and into a realm of infinite possibilities. The search for evidence of the multiverse is still in its early stages, but the questions it raises are profound and inspiring. We've talked about the edge of the observable universe, the cosmic horizon beyond which light hasn't had enough time to reach us. But this horizon isn't a fixed boundary in space, like a wall marking the end of the universe. It's a dynamic, ever-shifting boundary that depends on your location and the universe's expansion. Imagine a ship sailing on an ocean. The ship's horizon represents the farthest point the sailors can see, limited by the curvature of the Earth. As the ship sails forward, its horizon expands, revealing new stretches of water. Similarly, our cosmic horizon expands as time passes, and light from more distant regions of the universe finally reaches us. However, the universe's expansion throws a wrench into this simple picture. The expansion of space itself stretches the very fabric of the cosmos, carrying galaxies away from us like raisins in a rising loaf of bread. This expansion-driven recession velocity can exceed the speed of light beyond the Hubble horizon. The cosmic speed limit applies to objects moving through space, not to the expansion of space itself. The fabric of space-time itself is not bound by the same rules. Imagine traveling through space, past countless galaxies clustered together in magnificent cosmic webs, and then encountering a region where galaxies are few and far between, like tiny islands scattered across an immense dark ocean. These are the cosmic voids, vast regions of space, hundreds of millions of light-years across, that are remarkably empty, containing far fewer galaxies than the cosmic average. These voids are not completely empty, however. They are thought to contain dark matter, the elusive substance that makes up the majority of matter in the universe, but doesn't interact with light, making it invisible to our telescopes. The existence of these voids provides further evidence for the key role that dark matter plays in shaping the universe's large-scale structure. According to current cosmological models, dark matter acted as a gravitational scaffold in the early universe, its gravity pulling in normal matter and causing it to clump together into galaxies and galaxy clusters. The voids in this picture represent regions where dark matter was less concentrated, leading to a lower density of galaxies. If the universe is truly infinite, as some theories suggest, then wouldn't we expect to see galaxies everywhere we look, no matter how far away? The presence of these voids seems to imply that there are limits to the distribution of matter in the universe, even on the grandest scales. Some physicists have even speculated that the existence of these voids might be evidence for the influence of other universes, their gravitational pull tugging at the fabric of our own cosmos and creating these regions of lower density. Others have proposed that the voids might contain exotic forms of dark energy, the mysterious force that is causing the universe's expansion to accelerate. This dark energy, they suggest, could be pushing matter away from these regions, creating the observed void structures. By studying the properties of these voids, their size, shape, distribution, and the faint whispers of radiation that pass through them, astronomers hope to learn more about the nature of dark matter, the evolution of the cosmic web, and perhaps even the existence of other universes beyond our own. These studies require incredibly sensitive telescopes and sophisticated data analysis techniques, as astronomers are essentially looking for the absence of light, trying to map the shadows cast by these cosmic voids against the backdrop of the early universe. The study of cosmic voids highlights the interconnectedness of the universe, how even the seemingly emptiest regions can provide valuable insights into the fundamental laws of nature and the processes that govern the cosmos's evolution. As we continue to peer deeper into the universe's depths, mapping the cosmic web with ever-increasing precision, we can expect to uncover more surprises and challenge our preconceived notions about the nature of reality. The journey of cosmic exploration is far from over, and the most exciting discoveries may still lie ahead, hidden within the vast enigmatic realms beyond the void. We've journeyed to the edge of the observable universe and contemplated the mind-boggling possibility of a multiverse. But what if the universe, instead of expanding forever, eventually reverses course? What if, under the relentless pull of gravity, the expansion slows, halts, and then contracts, pulling everything back together in a cosmic rewind? This is the unsettling yet captivating scenario envisioned by the Big Crunch hypothesis, a cosmological model that proposes a dramatic end to the universe as we know it. Galaxies, currently rushing away from each other, slow down, halt, and begin to draw closer. The space between them shrinks, compressing the very fabric of space-time. The universe, once vast and expansive, becomes increasingly dense and hot, like a pressure cooker with the heat turned up to 11. Stars, squeezed together by the relentless cosmic contraction, begin to collide and merge, creating bizarre and short-lived stellar behemoths. As the universe contracts further, temperatures continue to soar. Radiation, once a faint whisper from the early universe, intensifies, bathing everything in a searing cosmic glow. The cosmic microwave background radiation, currently a faint echo of the Big Bang, would become increasingly energetic, its wavelengths shortening until it transforms into a blinding bath of gamma rays. Black holes, those cosmic gluttons, would feast on the surrounding matter, growing ever larger and more powerful. As they merge and coalesce, they would warp space-time to an extreme degree, creating gravitational whirlpools that distort the very fabric of reality. Life as we know it would cease to exist long before the universe reached this point of ultimate compression. The increasing temperatures and radiation would render planets uninhabitable, sterilizing any remaining life and leaving behind only barren, scorched remnants. Eventually, the universe would reach a point of infinite density and temperature, a singularity where all matter and energy are compressed into a single, infinitesimal point. This is the Big Crunch, the mirror image of the Big Bang, the end of space and time as we know it. What happens at the crunch point, and whether anything can exist beyond it, remains one of the biggest mysteries in cosmology. Some theories suggest that the universe might bounce back from the crunch, expanding outward once again in a new Big Bang, creating a cyclic universe with no beginning and no end, just an endless series of expansions and contractions. Other models propose that the crunch might lead to a completely different state of existence, perhaps a universe with different physical laws or dimensions, or even something beyond our current understanding of physics and cosmology. However, current cosmological observations suggest that our universe is unlikely to end in a big crunch. The expansion of the universe, instead of slowing down, appears to be accelerating, driven by dark energy. Some theoretical models suggest that the universe might have undergone multiple cycles of expansion and contraction in the past, with each cycle leaving behind subtle imprints on the fabric of space-time. These imprints, some physicists believe, might be detectable in the cosmic microwave background radiation, the afterglow of the Big Bang. The search for these cosmic echoes is ongoing, a testament to human curiosity and our relentless pursuit of understanding the universe's mysteries. Whether or not we ever find definitive proof of a cyclic universe, the very act of exploring these mind-bending possibilities expands our understanding of the cosmos and our place within it. The journey of cosmic discovery is a never-ending adventure, and every one of us is a part of it. Thank you for watching Time Pilgrimage, and as always, please remember to subscribe and like. If there is a topic that you would like to explore, please drop a comment.